Hello everyone. In this video we are going to talk about limits at infinity. Whereas last section we were talking about limits of infinity, where infinity was possible as our limit answer, this time we're going to talk about as limit as x approaches infinity, or as x approaches negative infinity. So it's very similar, but not quite the same. But all of our limit properties still apply. So as x approaches infinity for our rational graph here, which means as x gets infinitely large, or keeps being larger and larger of our x, that means we're approaching this graph from the left. And as we get larger and larger in our x, what number does it approach? Well, that would be 0, isn't it? It would approach 0 on our y's. This is not always the case, but it is a good gauge of thumb. So even though the limit as x approaches 0 is infinite, and the limit as x approaches infinity is 0, this is not always going to be this case. It doesn't go back and forth like that. But it is fun. So let's take a look at the next one. The limit as x approaches negative infinity. Now it is interesting to note we can't really do left and right with an infinite limit, because, well, you can't really approach infinity from anywhere but one direction. So if we're approaching x of negative infinity, we have to approach from the right. That's the only way it works. So as we approach negative infinity, our limit will be 0. And as we approach positive infinity, we must do that from the left. We will get 0 again. Now this is very interesting in that we will now see kind of that we have this invisible line here at the y-axis of y equals 0, otherwise known as the x-axis, my bad. And this is a horizontal asymptote of the function. So we can see it not just in the graph itself, but in the limits as well. Now I said that the limit properties still apply, and they do. Even though we're talking about limits as x approaches infinity, all those properties still apply, as well as all of the math that we have studied up to this point in various classes. So let's take a look at this example 3 here. We want to find the limit as x approaches positive infinity and x approaches negative infinity, and we're doing this with a polynomial. So polynomials, we can use the leading term test to figure out their end behavior, even if we don't know anything else, even if we don't have our calculator, and we can still find the limit. So this is an odd function. X to the 5th power is an odd function, and we have a positive leading coefficient. So I know, because I know and remember my end behavior, that this graph will go down on the left and up on the right. Even though I don't remember anything in the middle, I do know those two things because I know about the end behavior. So I can answer the limit as x approaches negative infinity and the limit as x approaches positive infinity, because I know its end behavior. So I don't even have to have my calculator. Woohoo! So as x approaches negative infinity, going down, we will have a negative infinity for our limit. Keeps going down. And as x approaches positive infinity, we keep going up, so that gives us infinity for our limit there. So just because we are finding limits as x approaches infinity does not mean that our limit itself cannot be infinity. That's perfectly valid. Okay, so what about example 4 here? We have the limit as x approaches infinity of 9 plus 10 over x squared. Well, if you remember from our section 2.3, I believe, we had one of our limit properties tell us that if you have adding functions like this, that you can split them up and it will be the same either way. So the limit as x approaches infinity of 9 plus the limit as x approaches infinity of 10 over x squared will still be the same thing as the complete limit of both. So anytime we have the limit of a constant function, well, that's just going to be the constant itself, because there's no reason for it to change. And then the limit as x approaches infinity of 10 over x squared, this is a rational graph, and so we have to stay away from 0 in our denominator. You can either graph it in your calculator if you wish, or you can remember that rational graphs all look pretty much the same, and that would be something along the lines of that and that-ish. So my limit as x approaches infinity of this rational graph would be 0. So my limit overall of 9 plus 10 over x squared would be 9. So the limit properties still apply no matter what. Even though we had to split it up, we can still find the limit itself. No problems. We can use the graphs, we can use the properties, we can use what we learned in previous classes. All of that mathematics still applies. We're just building on what we already know. So the last thing we're going to talk about in section 2.5 is something that you may or may not recognize, and they're called sequences. So a sequence or a series is an infinite ordered list of numbers that is often defined by a function. Actually, that should not say that, should it? That is defined by a function, or can be defined by a function. Maybe a better way to put it. Because we can write it as a list, a set, just like we do in this lovely example. The set of all even numbers, we can say 2, 4, 6, 8, or we can write it as a function itself as f of n equals 2n, where n is a natural number. Natural number is that double n there. So we can apply the limits and all the properties of the limits just as we do to functions and just as we do to ordinary limits. So think about what we know about even numbers. If we want to find the limit as n approaches infinity of the even numbers, well, does the even number set ever stop? Does it ever end? Does it ever approach any other number? Or does it just keep going? Well, it just keeps going. It just keeps getting bigger. And we can see that in here as well. So this is just another way of writing what we already know. The even number sequence just gets infinitely big, as well as the odd number sequence. Both just get infinitely large. Now that's not always the case because, well, not always do we have a sequence that is so easy and nice to deal with. So let's have something that's not nearly as nice. So let's find the limit as n approaches infinity of 22 over n. So n is assumed to be a natural number. A natural number being you start at 1 and you keep going into the positives, whole numbers. So for this, let's just make this easy on ourselves. And if n is 1, well, let's do this as a table, shall we? That'll make it a little bit easier. So n equals some number, and then what is that number? So what's the sequence? Okay, so if n is 1, we're going to get 22 over 1, which is 22. So if n is 2, 22 over 2 would give us 11. If n is 3, that would be 22 over 3, 22 thirds. N is 4, that would be 22 over 4, otherwise known as 11 halves. Alright, what about 5? We would get 22 over 5. Then 6, 22 over 6, otherwise known as 11 thirds. And we could just keep going. Now, fractions are fine, but sometimes it's not as easy to kind of picture it in our heads, is it? So let's just go ahead and get the decimal forms of these just to make it easier on ourselves. So 22 over 3 is 7.3 repeating. 11 halves is 5.5. 22 fifths is 4.4. 11 thirds is 3.6 repeating. And assuming we would just keep going, wouldn't it? So let's pick a big N just to have some fun. So let's have a jump and let's do 10. How about that? So 22 over 10 would give us 11 fifths. So 11 fifths is 2.2. So that's even smaller. So there is kind of a thing that it looks, well, we can easily see that it's getting smaller and smaller and smaller, but it's not really approaching a set number, is it? So let's try a bigger n. How about 20? Well, just keep going, right? So 22 over 20 would be 11 tenths, which is 1.1, still getting smaller. About 30. So 22 divided by 30 would give me 0.73, where the 3 repeats. That's better. Seems like the decimals are getting closer and closer together. So let's do a big one. How about 50? So 22 divided by 50 is 0.44. Full stop. It's 22 divided by 100. Give me 0.22. Okay, I can pretty much make some assumptions here, can't I? So, if my n keeps getting bigger, which is what this lovely chart is saying, right? If n keeps getting bigger, then what is my sequence going towards? We keep getting smaller and smaller and smaller, but we never go into the negatives, so that tells me that my limit as n approaches infinity of 22 over n would give me 0.